and she is going to tell us about the Calabi problem for Fano threefolds. Thank you.
Thank you. So first of all, I would like to thank the organizers for setting up and organizing this very nice program, and also for the invitation to give a talk. So today I would like to report on a results of a joint project with several people, Ana-Maria Castravet, Ivan Cheltsov, Kento Fujita, Anne-Sophie Kaloghiros, Süss Martinez-Garcia, Constantin Shramov, Hendrik, Süss, and Nivedita Viswanathan. So this is about the Calabi problem for Fano threefolds. And I would like to as an acknowledgement, say that this is a result of a project that started as a working group in the AIM workshop on case stability in January 2020. So back then we started to work a few examples, and then now I would like to report on what we have achieved so far. So let me start by reminding you of the Calabi problem. So this was already discussed in the lectures of Liu and Jung, and also in the talk of Bloom on Tuesday. So the Calabi problem asked whether a given compact Kähler manifold admits a Kähler-Einstein metric. So this is a metric whose rigid tensor is proportional. It's a constant times the metric itself. And here there are three very different cases when the this constant multiple is negative, 0, and 1. And this condition already implies that the first Chern class of X, or the anti-canonical class, has a definite sign. So the problem naturally divides into these three cases: the case of canonically polarized varieties, zero first Chern class, and positive anti-canonical class, which is the case of Fano manifolds. So for the first two classes, the problem has been solved by Oban and Yao. And for the last one, which is the one that we are interested in, then the problem is trickier. There is no definite answer to this question. And so there are some known obstructions to the existence of Kähler-Einstein metrics. And the first one is a very old one by Matsushima, that says that if a Fano manifold admits a Kähler-Einstein metric, then the automorphism group of X is reductive. So this already gives us some examples, some negative examples to the Calabi problem in dimension 2. So let me recall that in dimension 2, we have a well-known classification of del Peso surfaces. So these are P2, P1 cross P1, and then P2 blown up at most 8 points in general position. So in these cases, for the blow up of P2 in 1 point and the blow up of P2 in 2 points, then it's actually easy to compute the automorphism group. So this can be viewed as the automorphism group of P2 that fixes a point, and in the second case is that fixes 2 points or swaps them. And these are both this automorphism group are not reductive. So as a consequence, we see that in these two examples, the surface, the del Peso surface, does not admit a Kähler-Einstein metric. And conversely, Tian proved in 1990 that all other del Peso surfaces are Kähler-Einstein. So we would like to have a similar result for Fano threefolds. And so the Calabi problem for Fano threefolds asks if we can have such a classification. So I recall that there is this well-known classification of Fano threefolds by Iskovskikh, Mori, and Mukai. So there are 105 deformation families of Fano threefolds. And now maybe here I would like to share with you something else. So let me stop sharing this one and share something else. Probably I should first open this. Sorry, let me try this again. So I want to share with you this very nice web page, which is called Phonography. So this is actually a very good way to find quickly information about Fano threefolds. So here, here you can go through it. There is the identifier as in the Mukai, Mori and Mukai classification, and then also gives you some information about the description of the Fano threefolds, and also about its automorphism group. And then you can click, if you click in a family, then you get a little bit more information about each of this Fano families of Fano threefolds. So let me stop sharing this one and go back to my slides. Okay, so we have this 105 deformation families, and then we would like to know which Fano manifolds are Kähler-Einstein. So maybe I could divide this, if I see this as a long-term project, I would divide it in say 3 parts. So the first part, for each of the 105 deformation family, to determine whether the general member is Kähler-Einstein. And then of course, we would like to maybe know a little bit more. So for each family, maybe we want to determine exactly which members are Kähler-Einstein. And then finally, with all this exciting new results about moduli spaces of K-semi-stable Fanos, then maybe in these cases, we would like to understand their moduli spaces and semi-stable degenerations. So in this talk, I will really only mostly talk about the first problem, which is the one that we have been able to solve. So now we know that in each family, whether the general member is Kähler-Einstein or not. For the second problem, actually, I should say that for 71 of the 105 families, we can say exactly which members are Kähler-Einstein and which ones are not. So this, but this is still not. There's still some families for which we don't know the answer. Although in most cases we have a very explicit conjecture on which ones are Kähler-Einsteins and which one are not. And then I will say nothing about the third problem. Okay, so first I should say that when we started working on this, there were roughly a bit more than half of these cases were already known. And so I apologize in advance that I will not be able to give proper credit for everyone that contributed to this problem, but let me just discuss a few known cases. So of course we have the cases when the automorphism group is non-reductive, and then we know that they're not Kähler-Einstein. In many cases, these are products, and then we have, and so they were also already known. Also for toric varieties, many of these Fano threefolds are toric varieties, and for toric varieties, there is a very neat characterization of the existence of Kähler-Einstein metric, which is that the barycenter of the corresponding polytope is at the origin. So for toric varieties, we have 18 toric Fano threefolds, and 5 of them are Kähler-Einstein, and 13 of them are not Kähler-Einstein. And also another class of manifolds for which the answer was known is cyclic cover. So there are techniques by first Araujo, Gigi, and Pirola, and then more recently by Dervan to treat these cases. And also there are some sporadic cases that were also known. And a very interesting one is this family 110. So these are also known as V22. So these are Fano threefolds of genus 12. So they are, let me just give you a brief description of this manifold. So you can, if you take the vector space C7 and then you fix a linear map from wedge 2 of V to C3, non-degenerate map, then you can look at the subvariety of the Grassmannian of three-dimensional spaces in this seventh-dimensional vector space that is isotropic with respect to this map. So this is a description of the Fano threefolds in the family 110. And now, depending on your choice of this linear map, you get different. So this is, I think, if I'm not mistaken, a six-dimensional family. And there is in this family there are some spatial members. So there is one element with automorphism group non-reductive. So of course for this one we know that it's not Kähler-Einstein, and there is one special member, a unique member with very large automorphism group, PGL2C, and this is the Mukai Uemura Fano threefold. And so this is already known that for these the member with non-reductive automorphism group, so it's not Kähler-Einstein, and then the Mukai Uemura admits a Kähler-Einstein metric. And so this actually was the first family for which we see this type of behavior, that for some members of the family, some members of the families are Kähler-Einsteins and others are not. And later on, actually, there is also an important example that worked out by Tian of one element in this one member of this family with finite automorphism group that again does not admit a Kähler-Einstein metric. So this was an important example because it answered negatively a folklore conjecture then that the finiteness of the automorphism group should be equivalent to Kähler-Einstein. And in this is the family. This is the one of the families for which we do not know the complete classification. Donaldson has long-standing conjecture about which members of the family are Kähler-Einsteins and which are not. And it seems that, so from our experience in working with these families, it seems that this one is really still the hardest family to completely solve Calabi's problem. Okay, so this was a little bit of the known results, and now we are going to turn to the tools that we have been using to address this problem. So let me start by discussing this Yao, Tian, Donaldson conjecture. So this was already presented by Liu and Jung in their lectures. So here, let's start with a K-Fano variety. So this is, so here I'm assuming that the Fano has KLT singularities. Let me just remind you what was already introduced in the lectures, that a test configuration for X is just a GM equivariant flat family over A1, together with a GM invariant pi ample line bundle, such that over the punctured line, this is just a product of our Q-Fano variety X with some multiple of the anticanonical divisor. And so here, this is the nice picture from Liu's first lecture, that this is illustrating a test configuration. And to such a test configuration, we can attach a invariant, the Futaki invariant or Donaldson-Futaki invariant that, so it was first defined analytically, but now this turns out that this is an algebraic invariant of the test configuration. So it can be defined in terms of weights of the actions or in terms of intersection numbers. And let me also recall the definitions regarding K stability. So X is K semi-stable if the Futaki invariant is non-negative for every test configuration. It's K stable if the same holds and equality is equivalent to the test configuration being a product type. And X is K polystable if it is semi-stable, and if you have equality in the Futaki invariant, then this forces this special fiber to be isomorphic to X. And then the theorem by Chen, Donaldson, Sun, and Tian says that for a smooth Fano variety, the existence of Kähler-Einstein metric is equivalent to K polystability. So even though we are interested in classifying smooth Fano threefolds that admit Kähler-Einstein metric, we actually use all this theory also in the singular setting, as I will explain soon. Okay, so let me just a couple of remarks. So first of all, again, this was already discussed in the lectures. If a Q Fano variety is K-stable, then its automorphism group is finite. And if the automorphism group of X is finite, then K stability is equivalent to K polystability. Okay, so now let me discuss some other results that we will need, which is the behavior of this K stability conditions in family. So let's assume that we have a flat family of Q Fano varieties. Then you can look at the locus of the base consistent of points whose fibers are K-stable. And this is a Zariski open subset of the base. The same for K-stability, the set of points in the base over which the fibers are K semi-stable, again, is Zariski open. And for K polystability, the set of points with whose fibers are K polystable are constructible. So this is, okay, so when we apply this, we will apply this because we are interested in understanding whether the general member of the family is, say, K polystable or Kähler-Einstein or K polystable. And so if we prove that there is an element, there is a member that is K stable, then automatically we get that the general member is K polystable, and then in particular has a Kähler-Einstein metric. And something else that we use, and another important property, is the uniqueness of K polystable degeneration. So that means that if I have the same family, a same family of K polystable objects that degenerating to some K polystable objects, then these degenerations have to be isomorphic. So these results are due to Bloom-Liu, Bloom-Liu-Shu, and Bloom-Shu. And okay, and so now let me recall the first evaluative criteria that was again also explained in the lectures. So here we fix X a K Fano variety and a divisor over X. So that means that I have a birational proper morphism from Y to X and a prime divisor E on Y. Then let me recall the definition of the log discrepancy of the expected vanishing order that was also defined in the first lecture of Liu. And here I wrote here this integral from 0 to infinity, but as has been explained, this integral is finite, and that it can go from 0 to tau, where the tau is the pseudo-effective threshold of E. And now we define the beta invariant of E to be the log discrepancy minus the expected vanishing order. And then there is this important theorem by Fujita and Lee that says that X is K semi-stable if and only if the beta invariant is greater or equal than 0 for every divisor over X. And X is K stable if and only if the beta invariant is positive for every divisor E over X. So here it may seem difficult to apply this theorem because we have to test every prime divisor over some model of in some model of X. But it turns out that in many cases, this gives a very good way of answering negatively the Calabi problem. So namely, there is this definition due to Kento Fujita that says that a Q-Fano variety is divisorially unstable if there is a prime divisor E on X itself, not over some model, for which the beta invariant is negative. And let me say that this is to compute this beta invariance is something completely doable. So this Fano threefolds, so in the Iskovskikh, Mori and Mukai classification, they are very well understood. So in many cases, you know, I would say in most cases, you know exactly what is the cone of effective divisor, the cone of NIF divisor. So you can write down and compute this this beta invariant very explicitly. And so for if a Q-Fano variety is divisorially unstable, then automatically, of course, it is not K polystable. And so it does not admit Kähler-Einstein metric. And Fujita actually gave a complete classification of divisorially unstable smooth Fano threefold. So he went through the list, and whenever he saw some suspicious divisor, he computed its beta invariant, and then so what he got is that all members, the divisorially unstable Fano threefolds are exactly all the members of 26 out of the 105 families. So for those, we already know that they are not K polystable. And so this is, and now maybe I can state our main theorem. So what we show is that if X is a general Fano threefold in one of the 105 deformation families, then X is K polystable, the general member is K polystable, except either if F is one of the 26 is one of the 26 deformation families that were characterized by Kento Fujita, or it is the family Chu26, which I will explain shortly. So what we are seeing here is that Fujita's criterion, this divisorially unstable condition, was able to find almost all the non-K polystable, generically K polystable families. So let me explain now what is this family Chu26. So this family actually has only two members, one of which degenerates to another. And as is typical in this Mori and Mukai classification, we can completely describe this Fano threefolds by giving their extremal ray contraction. So this first index, the Chu, says that this Fano manifold has Picard rank Chu, and these are the Chu extremal ray contractions. So this Fano manifold X can be given in two ways as a blow up. So if you look to the left of the diagram, you can write X as a blow up of a smooth quadric threefold. And if you look at the right part of the diagram, then it can be written as the blow up of this Fano variety V5. So V5 is a linear section of the Grassmannian G25 of codimension 3. And even more, if you look to the right side, this is the blow up of the quadric along a twisted cubic curve. And for the right-hand side, this is the blow up of a line in the Fano threefold V5. Now this Fano threefold V5 is very well studied. So the Hilbert scheme of lines, conics, and twisted cubics are completely well understood. And in this case, let me distinguish the two members of this family by looking at its realization of the blow up of V5 along a line. So the lines on V5, there are two types of lines on V5. So actually the Hilbert scheme of lines in V5 is isomorphic to P2. And there are there are two types of lines: the ones with trivial normal bundle O plus O, and the ones with unbalanced normal bundle O minus 1 plus O1. So this gives us if you blow up any line of type of the first type, you will get isomorphic threefolds, and same thing for the second one. And so we get these two members, and it's actually by understanding the automorphism group of V5 that fixes a line, you can just compute the automorphism group of these two members. So for the first one, the automorphism, at least the connected component of the identity of the automorphism group of GM, and the other one is, again, non-reductive. So for the second one, this is not K-polystable. But actually even more, we can compute some beta invariance of the visors over X to actually show that it's not K semi-stable. So this is a sort of the bad guy in this family is not even K semi-stable. And now let's consider now we want to discuss the other member. And so now we are going to rephrase this condition on the normal bundle of the line in terms of now the left-hand side of the diagram. So our twisted cubic lies in a unique hyperplane section of the three-dimensional quadric, which I'm calling H. And the condition that the normal bundle of the line in V5 is balanced, it's O plus O, is equivalent to saying from this other perspective that the hyperplane section containing the twisted cubic is smooth. And so this is the case that we are interested in. And so we can actually write down quite explicitly our variety X by writing down the quadric, the twisted cubic, and then blowing up. And actually this allows us to construct a certain degeneration of this Fano variety X1 as follows. So first I take the degeneration of my smooth quadric, GM equivariant degeneration into a singular quadric in such a way that the limit of the twisted cubic does not pass through the singular point. And now I can blow up the twisted cubic in all the fibers. And in this way, I get a family whose general member is the threefold we are interested in, X1, and it degenerates into a singular Fano threefold, which is the blow up of the singular quadric along the twisted cubic. And so, in other words, what we constructed was a special test configuration for our variety X1. And this special fiber, this degeneration X0, is a Q-Fano variety. And because everything is so explicit, you can actually compute its automorphism group, and its automorphism group contains, for instance, an action of the GM semi-direct product with a cyclic group of order 2. And so this is what we call a complexity 1 T variety. And for those varieties, so for complexity 1 T varieties, one can use the theory of T varieties to describe Futek invariants. And so there is a whole machinery that allows us to actually show that in this case, this singular Q-Fano is K-polystable. But now notice some conclusions from this. So we found a special test configuration whose special fiber is a K-polystable Q-Fano. So from the fact that K semistability is open, then we conclude that our Fano variety is also K semi-stable. And from the uniqueness of K polystable limits or K polystable degenerations, what we conclude is that our X1 cannot be K polystable. So this is how we prove that this, in fact, every member of this family 226 is not K polystable or not Kähler-Einstein. Okay, so this is, so now this is, I explained to you how we prove that something, that the general member of a family is not K polystable. So this, for this we use this beta invariant. And now let me explain to you the tools that we use to give positive answers to the Calabi problem. So this is, so let me go back to the, and describe some more, some more instances of the evaluative criteria for K stability. So again, X is again a Q-Fano variety, and E is a divisor over, prime divisor over X. Again, here we have the definition of the log discrepancy, the expected vanishing order, and the pseudo-effective threshold. Now there is another a very important invariant attached to a kind of a Q-Fano variety that was first introduced by Tian, which is the infimum of the log canonical thresholds of pairs XD, where D runs over all effective Q divisors that are Q linearly equivalent to minus K. So this is the alpha invariant. And we also, let me also introduce the delta invariant, or this is sometimes also called the stability threshold, which is the infimum for all divisors E over X of the log discrepancy divided by the expected vanishing order. And these invariants, alpha and delta, they are related. They satisfy some inequalities. And now let me explain the criteria. So this is a result of work of several people. So first of all, if the alpha invariant is greater than n over n plus 1, where n is the dimension of n, then X is K stable. And then, but let me just, well, I will observe later that this bound is not sharp, and you cannot use it to characterize K stability in any way. But for the delta invariant, we know that it's if it is greater than 1, then X is K stable. And it is greater or equal than 1 if and only if X is K semi-stable. And let me just remark, so this is the remark that I wanted to say, that the alpha invariant that has been very much used to prove K stability, but it does not always work. So for instance, this is an easy example. When X is the projective space, then the alpha invariant one can compute. This is 1 over n plus 1. And in fact, this is the Pn can be characterized as the Fano with the smallest alpha invariant. And so one cannot hope to always use the alpha invariant in general. So what we are going to do instead is the following. So we are going to explore symmetry. So as I said, for the moment we are into, so our first aim is to prove or disprove K polystability for the general member of the family. So it is enough to show K polystability, or at least K stability for one special element, and then we can conclude by openness of K stability. So here, so let's consider a Fano then having some symmetry. So let's fix G, a reductive group inside the automorphism group of X. Then we have G equivariant versions of the alpha and the delta invariant. So for the alpha invariant, the G alpha invariant of X is the infimum of the log canonical thresholds of this pairs 1 x 1 over m times d, where d is some sublinear system, G invariant sublinear system of some multiple of the anticanonical class. So here I should say that if you know more about your group, then it's actually it's enough to consider the infimum of the log canonical thresholds. In some cases, for some groups G, it's enough to consider the infimum of the log canonical thresholds of pairs XD for G invariant effective divisors linear equivalent to Q linear equivalent to K. And also we have the G invariant delta, so the delta G of X, which is the infimum again of the log discrepancy over the expected vanishing order. But now we only consider divisor over X that are G invariant. So either they are G invariant on X, or once you take a lifting of the action. So now let me state the criteria that we use. So first of all, so I mean, again, this is a long list of people that contributed to these results. In our case, when X is smooth, then the alpha G, if the alpha G of X is greater or equal than n over n plus 1, then Kx is K polystable. And so here I should say that this allows us to prove K polystability of many members of our family. I mean, this is this G invariant log canonical places have been much studied, and there are many tools to investigate them. So this actually proves very useful to prove generic K polystability for many families. And then and also, if we know that the delta G invariant, the delta G of X is greater than 1, then again X is K polystable. Okay, so these are the two criteria that we or some of the criteria that we use in our work. And so so as I said, there are tools to study G invariant log canonical places. So in our cases, usually we have a Fano threefold, and we choose one in the family with a big symmetry group G. And in many cases, this group is big enough so that we don't have any invariant points. And well, if you have an invariant divisor, then again, this is easy it's easy to compute all this, the log canonical threshold and the expected vanishing order and the beta invariant. So these are also okay. And so usually we are left to deal with G invariant curves on our threefolds. And so for those, actually we use this very powerful machinery by Martinez-Garcia theory of admissible flags to estimate this delta invariant. So here by delta Zx, I mean that I want to understand the infimum of this quotient for all prime divisors whose center contains a given subvariety Z. So usually in our case, these Z are going to be the J invariant log canonical places for certain pairs. Okay, so let me end by giving you trying to work out one example that I find very nice, and it's not so hard to explain. So this is the family 222. So this family has one-dimensional moduli, and again, this has a very concrete description. The extremal rays are very simple to describe. So our X admits two realizations as blow-ups. So to the left, X can be given as the blow-up of P3 along a twisted quartic. So this twisted quartic is contained in a unique smooth quadric in P3. And also it can be, well, we will not use it here, but just for completeness, let me say that this X can also be given as the blow up of V5. V5 was, again, a codimension 3 linear section of the Grassmannian G25, the blow up along a conic. And as I said before, the conics in the model, the Hilbert scheme of conics in this in V5 is very well understood. Okay, so this is our any X in this family can be given in this way, and so we can use this to. So let me here also fix the notation. So I'm calling denoting by E the exceptional divisor over the twisted quartic under the projection P to the left, and actually the other contraction contracts this strict transform of our quadric to the conic C. And here one can show that the automorphism group of X is the same thing as the automorphism group of P3 that stabilizes the twisted quartic. And again, this is isomorphic to the automorphism group of the quadric, the quadric surface that contains C4. And so in this case, the first remark is that we cannot use the G alpha invariant. In this case, we can write down explicitly what is the anticanonical class of X. And this is 2 times Q prime plus E. So we see here, and of course oops. Okay, so here we see that the both Q prime, Q tilde, and E are G invariant. And so in this case, we see that the alpha, automatically the alpha invariant of X is less or equal than 1/2. So we cannot use it to conclude polystability. So we have to compute delta G invariance. And so in order to do so, let's write down things very explicitly and find a special member of our family with a big automorphism group. So, okay, so let's write this down. So as I said, the automorphism group can be seen as the automorphism group of the smooth quadric surface that stabilizes the curve C4. This curve C4 is a curve of type 1,3 in the quadric, or in P1 cross P1. So it's given by an equation of this type. So actually, after making suitable changes of coordinates, you can always write the quartic curve in this form. And now here, we have a few cases to analyze. So here we can immediately find a very symmetric quartic curve, which is the one given by this equation. And this is when both A and B are 0. So if one of them, if either A is 0 or B is 0, well, up to change of coordinates, we can write this in this form. And then if both A and B are different than 0, then we can actually rescale and change coordinates so that it can be given in this way. So this is the equation of our quartic curve, and here we have A equals to B. So we have this lambda, and this lambda, well, we can assume it is different than 0. So 0 would be the first equation. It's different than plus and minus 1 because this would give us singular quartic curves, and different than plus or minus 3 because this would give us the second, well, after rescaling this would give us the second equation. So these are the some special, so these are the forms of our quartics. So okay, so now let's look at them more carefully. So first of all, in the first one, you see that it's very symmetric, and it's very easy to see that the automorphism group of the the threefold X naught, or which is the same thing as the automorphism group of the of the pair, the quadric and the curve. This is GM semi-direct product with the cyclic group of order 2, and also, so this is the only. So this is, as I said, this is a one parameter family, and this is the only member of this family with an infinite automorphism group. And also, in the third one, if you choose your lambda very carefully, in this case, this is a lambda plus or minus a square root of 3, then you get, again, the automorphism group is bigger than the usual one. So this is going to be the alternating group A4. So, and then what we do in these two cases, we compute, and okay, I should say that this is okay. This is not a straightforward computation. I mean, this is some pages of computations. Then you actually can compute in both cases. You can understand what are the possible G invariant curves in the non-KLT locus. And then we can prove that the delta, in both cases, the delta invariant is greater than 1, and so they are K-polystable. And so this proves using openness of K stability. So notice that the X, X, I wrote X2, it should be X square root of 3. The second one is has finite automorphism group. So in this case, K polystability is the same thing as K stability. And so we conclude that the general member of this family is, again, K polystable. But also, let me make a remark. So this is one interesting case when we also get some non-polystable, K polystable members, namely, let's look at the second equation of the curve of the quartic. So here I can plug in a parameter t, and then if t is different than 0, then this is again the same curve as the first one in blue. But if I make t goes to 0, then what I get is a degeneration of x into x naught. But we have seen that x naught is K polystable. So again, by the uniqueness of K polystable degenerations, we conclude that x is not K polystable. And so let me now stop sharing and share something else. So this is, let me. Sorry, I should probably have to open this first. Okay, now it should work. Okay, so this is showing you our table that summarizes our results. So this is a table, and so I'll just go through it very, very quickly. So the first, so to the left, we find the numbering of the Fano threefold according to the Mori and Mukai index. So we have a little description, and then here the important things are this columns K polystable and K semi-stable. So in many cases, so you see that when you have a yes, it means that every member of the family is K polystable. And here, well, it's K semi-stable. Then there are some cases which are these ones here with a star. So yes, star means that the general member of the family is K polystable, but we do not know whether all members are K polystable or not. And then in some cases, when you find an exist a no, means that, well, in this family, there is the general member is, yes, K polystable, but there are members which are not K polystable. So I will just go through very quickly the table so that you can have an idea of Okay, so these are, so I will show you the families that I explained to you. So I explained to you this family here. And also the 226, this family here. Okay, so these are our resulting table. Sorry, there are some misprints in the middle of the table. Just please ignore that part. Okay, so these are so this is just a summary of our results. So let me stop sharing. And now, okay, so now this is what I wanted to tell you today. So I thank you very much for your attention.
Thank you very much, Carolina. So do I read correctly? It's a 420-page manuscript?
Yes, for the moment.
For the moment, I see. Does anybody have any questions for Carolina? Okay, if there are no questions, then let's thank Carolina again.